Um, so, so we've talked about several kinds of surfaces so far. We've talked about planes. We talked about spheres. We talked about cylindrical surfaces the other day, and we talked about quadric surfaces the other day. We're going to talk about the fifth type, special kind of surface that we're going to talk about is surfaces of revolution. We've done some work in the past with surfaces of revolution. We know how to find the volume of a solid of revolution, and the surface of revolution would be the boundary of that volume. We know how to find the arc length. We know how to find the surface area. So we've worked with these surfaces before, but now we're going to work with how we write an equation for them, how we kind of analyze them in space. So let me draw a picture, and we'll kind of to motivate how we're going to work with these. So here are our coordinate axes, our normal right-handed coordinate system. And if we have some surface or some curve here in the YZ plane, we have some kind of curve, and we're going to say that this curve is given by y equals some function of z, and I'm going to call it r of z. So a point on this curve is going to have the coordinates. We're in the YZ plane. This point is going to have the coordinates 0. The y coordinate is given by our function r of z, and the z coordinate is just z. If we revolve this point about the z-axis, so we're going to revolve that about the z-axis. The radius, when we revolve that point, it's going to give us a circle. So as this point travels around the z-axis, it's going to travel in this circle as we revolve it around the axis. So the point describes a circle. The point moves through a circle. And the radius of that circle is just our function, r of z, our y coordinate. And if we join together all these points as we revolve this curve around the z-axis, we get a surface. Parallel to the xy plane, we get these circles with radius of r of z. So parallel to the xy plane, we have these circles. So the equations of all these circles, if I projected this down into the xy plane, the equation of that circle is, if I'm just visualizing projecting it down into the xy plane, is x squared plus y squared equals the radius squared, r of z squared. This gives us our equation for our surface. So any point that's on our surface is going to have this equation if we project that circle down into the xy plane. Any of these points, any point that's on that surface is going to satisfy this equation, because as we revolve it around the z-axis, it travels around in this circle that's parallel to the xy plane. So that's going to be our equation for our surface of revolution. Any surface of revolution, if we revolve it about one of the coordinate axes, is going to have an equation that looks like this. If we generalize this argument for revolving a curve about any one of the three axes, we get three cases. So these were revolving about the coordinate axes. So, and I'm going to say we have a radius function r. And our equation, for the equation of a surface of revolution, is, so my first case, we're going to revolve about the x-axis. We get y squared, our equation is going to take the form y squared plus z squared equals sum r of x squared. Our radius function is going to be a function of x to revolve about the x-axis. Our second equation, if we revolve about the y-axis, we get x squared plus z squared. It should be squared. Equals our radius function as a function of y squared. And in our third case, if we revolve about the z-axis, we get x squared plus y squared. The case that we looked at as our example, x squared plus y squared equals some radius function of z squared. And these all come from looking at a curve in one of the coordinate planes and visualizing a rotation, so we get it. We're rotating, and each point on that surface revolves in a circle about the axis. So these are all just equations of circles about one of the coordinate axes, and our radius varies with one of the other coordinates, because we have a curve in those planes. Does that make sense? So this gives us another family of curves, another family of surfaces that we can analyze, that we can visualize, that we have some tools to work with them now. So we know how to work with planes, spheres, the cylindrical surfaces and quadric surfaces. So these give us just a different kind of surface, and surfaces of revolution, because we can generate them with some interesting curve in the coordinate axes. It gives us a whole new kind of surface that we can work with. All right, let's look at a couple of examples of working with these surfaces of revolution. Any questions before we go on? Okay. So we want to find the equation for a surface. Someone asked me last year, they said, Mr. Beamer, why do you say we want to? He says, you always say we want to do this. So we want to find the equation for the surface. We're going to form it by revolving z equals the natural log of y about the z-axis. So when we revolve about the z-axis, we want our radius function needs to be some function of z. So the radius function needs to be a function of z. and I'm going to say some r of z. So we need to get a function in terms of z. So what are we going to do with our curve here to give us a function of z? We can rearrange this and say y equals e to the z. What? Yes, easy, just like I always say, right? So our radius function, we're just going to say our radius function, this is our r of z. R of z is e to the z. And then we can write our equation. So our equation of our surface, x squared plus y squared equals e to the 2z. E to the z squared is e to the 2z. And if I drew a quick sketch of this, what we would end up with is a surface that looks like here's our function y equals e to the z in the yz plane. Like so. And we're going to revolve it around the z-axis. So I'm going to extend this back here. And in this plane we have like so, and we have circles around this way. So it looks like kind of a giant funnel about the z-axis. So that would be our surface, kind of a funnel shape. Does that make sense? So this would be if we could arrange our trough, our parabolic trough that we were talking about yesterday. We could maybe have it dump the water into this infinite funnel. Right. Once the water gets in the infinite trough, we can empty the trough into this infinite funnel. All right. Any questions on that example? Okay. Let's for this one, let's revolve. Let's revolve 8x squared equals y to the third about the x-axis. So for this one, our radius function, what do we need our radius function to be a function? What variable do we need our radius function to be a function of? We need our function, we need r of x. So how are we going to write r of x here? Y equals 2x to the 2/3. We have to solve for y in terms of x. And then this is going to be our radius function. So now we can write our equation. So y squared plus z squared equals 2x to the 2/3 squared, right? So we could simplify or rewrite that. Y squared plus z squared equals 4x to the 4/3. And if we drew this one's a little harder to visualize. If we draw, I'm going to draw the x-axis more kind of this way. And our equation, our curve in the xy plane is kind of like so. Come back here. Something like this. And we revolve it around x-axis. So it's almost like the parabolic cylinder that we talked about the other day, and we're revolving about the x-axis. Now, one thing to remember about surfaces of revolution is that the generating curve is not unique. We could form this same surface by revolving z equals 2x to the 2/3 about the x-axis. So we looked at our generating curve in the xy plane. We could look at the generating curve in the xz plane, revolve that about the x-axis, and get the same surface. So we can pick our generating curve in any of the coordinate planes and get in different coordinate planes and get the same surface. So here our generating curve just happened to be we chose it to be in the xy plane. We could have the same generating curve with the same functional relationship between x and z in the xz plane, revolve that and get the same surface. So our generating curve is not necessarily unique. Questions on that one? Okay, let's look at one where we go the other direction. We want to do x squared plus y squared minus 2z equals 0. We want to find the equation of the generating curve. So we're given that this is a surface of revolution. We want to find the equation of the generating curve. So anybody have an idea how we might go about this? Move the 2z over. Since we have our coefficients on the x squared and y squared are 1, that suggests that let's write our equation for our surface of revolution in terms of x squared and y squared. So we say x squared plus y squared equals 2z. So what's given this form? What is our axis of revolution? Z is our axis of revolution. So our radius function, r of z, and I'm going to say r of z squared, from this r of z squared equals 2z. So r of z is going to be square root of 2z. And so how are we going to pick how can we pick our generating curve now? We could be in the xy plane, or the xz plane, or the yz plane. So we can pick our other variable as either x or y. So we can say our generating curve is either x equals, and I'm just going to write this as square root of 2z to the 1/2. Whoops, should be either x equals or y equals square root of 2z to the 1/2. Either of those generating curves will generate this surface of revolution. And if we graph this, if we sketched a quick graph of this, we get, anybody have an idea of what this looks like? Y equals square root of 2z to the 1/2. I could rearrange this, or x equals square root of 2z to the 1/2. I could square both sides, and I could say, let's say x squared equals 2z. What's that?
Could you just say z
Z equals
equals x squared over 2?
x squared over 2, and that is a parabola. So we end up with a parabola in our coordinate axes, and we revolve that around the z-axis, and we get a paraboloid. So this surface is also a quadric surface. So this quadric surface is a surface of revolution, and it's a quadric surface. So we can think of it as in two different ways, and analyze it in two different ways. And I told someone, after looking at all your sketches of your surfaces, everybody can do it better than I can.
Why is it going the opposite direction? If you have a z equals 2x squared.
Did I sketch my graph going the wrong way?
Is that right? No, that's right.
Yeah, I think this is right. Yeah, because when I'm confused about something like that, I always think, okay, think of x and y. So if we have y equals x squared, the axis of our parabola is the y-axis. That helps me figure it out. All right, any questions on surfaces of revolution? Okay. Homework. We're almost done with this chapter. Next thing we're going to talk about is cylindrical coordinates, and then we talk about spherical coordinates, and then we are finished with this chapter.
Do we have a different book than this?
No. Same book, yeah. So yeah, by the end of the year, you will be able to hold this book up and say, I know everything in this book.
Are we going to do a math for your shirts?
That's up to you guys.
Yeah.
You can design one.
We wanted Calc, right?
All right, there's your homework.